Okay, so right, so I want to talk about Skeins, tori, DAHA. So that's so some work with so Sam Gunningham. Bezerani. And Haiping Yang. But I also want to put that in some context about Langland's duality. Conjectures. So that's with Sam again, with Pavel Safronov, who's here with us today, and David Bensby. Okay. So we're going to be computing Skein modules on tori using the DAHA and confirming some recent conjectures in Langland's duality. Okay, so let me get started. I know that some people are familiar with Skein modules in various contexts. I want to recall for you the general definition that will appear. So let's fix three-manifold M oriented, a reductive group G, and a quantum parameter Q. So so I want to introduce, I'll also be talking about an oriented surface. Well, so first for a three-manifold, so first let me recall that if I have a ribbon graph, so I'll give you a cartoon of what that is, in a cylinder. So that's something like this. So a ribbon graph will have some ends possibly at the top and the bottom of the cylinder. These will be labeled by some objects category. So the objects here, U, V, W, X, Y, we can think of as, if we like, just representations of our group, finite dimensional representations. And then a ribbon graph is some sort of filling of this thing. Like so. So at every vertex that I've introduced, we're going to have a morphism. So F, G, H, let's say. These are going to have orientations on them that we can choose arbitrarily. So here, the F, G, H, these are going to be maps from the tensor product of all the incoming to all the outgoing edges. So for instance, if I have X, Y, let me orient that one this way, and Z here, then F, we've got Z coming in and X and Y coming out. So F would be a Hom from Z X tensor Y. Okay, so that's the notion of a ribbon graph in a cylinder. And we can, so the Reshtikin tribe evaluation gives us a map from the span. Yep.
Here Z is like tensor product of VW and U or no?
This Z?
Yeah, it comes from upstairs.
No, so Z, so right, so sorry, so the vertices at the endpoint, and indeed all the edges on the interior are labeled by some representation. And so this we think of the fact that this flows into the vertex means that we have Z as an input, and then the fact that X and Y flow out means that we have those as outputs. And then we have to attach some data, which is a morphism at the vertex.
Sorry, does it matter the order of the factor in the tensor product?
Yes, thank you. So I use this word ribbon graph. So some extra data which I'm suppressing is that these, if you like, there's a cyclic ordering at every vertex. People usually would indicate that by fattening these things up, and then you can't search them.
Sorry, then where does B live then?
Sorry.
Where does B live with Z on the outgoing arrow?
Good. So you're saying that so G would then be let's call this object A and B. So then G is a morphism from A tensor B to Z. So all the edges are labeled by representations of the group, and all the vertices are labeled by morphisms.
Vertices at the top with.
Well, you should think that these vertices at the top are the endpoints of an edge. So if you like, I'm labeling this vertex and these edges the same way. Yeah, thank you. Sorry, I wanted to give a sort of just a.
So B is the same as V.
Say again?
Is B and V the same then?
Yes, thank you. That one was already labeled. There you go. Okay. Thanks for all the questions. So the Reshetikhin tribe evaluation gives us a map from the span of ribbon graphs. So G colored ribbon graphs to palms from the tensor product of the let's say the tops. So in this case, E tensor W tensor U to X tensor Y. Okay, so far I haven't brought in the Q yet. There was this parameter Q here. Important point is that the Reshetikhin tribe construction works for any ribbon graph. So there's actually two categories that I want to consider. I can consider rep G, which is representations, say finite dimensional representations of the of my reductive group G, and there's another category called rep QG. So this is finite dimensional representations of UQG, certain ones. Rather than giving you a definition of this category and telling you all the structures that this category has, I can just say that the fact that the Reshetikhin Tarayev map is well defined depends on the fact that this has the structure of what's called a ribbon braided tensor category. So I'm basically assuming everybody here has seen quantum groups and is familiar with the idea that you have a braiding on the category of representations of the group. It also has what's called a ribbon structure, which is how you handle this cyclic orientation. And so the Reshetikhin tribe evaluation lets us take any ribbon graph that we draw in a cylinder, and we can interpret that as a morphism. So the HAMs now take place in rep Q G. Okay. That's just a quick reminder on what's called the graphical calculus. For braided tensor categories. Okay. So that's something that we can do locally in a cylinder. And then once we have that definition, there's two important modifications we can do. Let me here. So first of all, we can now talk about the Skein module. the three manifold. So this is going to be the span of ribbon graphs now embedded in M3. And let me emphasize closed ribbon graphs. So this three manifold had a boundary, and we allowed that the things could end at the boundary. And for a general three manifolds, we're gonna not allow that, so they have to close back up on themselves. And then we quotient by the relations. In every cylinder. Okay. So that is, we've got our three manifold. We've got something that locally looks like this network of things coming together. So the thing has to close up, it has no endpoints. And then the relations that we impose are just that if we ever see, for every cylinder, that in the three manifold, we apply the Rechteck and Tribe evaluation to that diagram, and any relations that we pick up, we impose on the entire vector space. So let me sort of give three orientations that will help. So the first one is that maybe an example. So usually when you see a Skeins talk, they'll just do the following example. So if G is SL2, then there's a lot of simplifications. So for SL2, so we have, first of all, we have that the weight one representation, the two-dimensional defining representation, is a tensor generator. So that just means that every representation, I can take tensor products of that, and then I can choose some projector and project down. We have Chervil duality. And we have that the dual of the defining representation is isomorphic back to itself, it's self-dual. And so these give a simpler calculus. So we can actually just consider, we can get rid of the trivalent vertices, and so we can just consider links by Chervil duality. We can get rid of the labels because we just label everything by the tensor generator, and we can get rid of the orientations because it's self-dual. And so then we just get the span of links modulo the Kaufman relations. So let's say that if I ever have a crossing, this is equal to q to the 1/2 times this, plus q to the -1/2 times this. And the unknot is equal to q plus q inverse. Those are the Kaufman relations. I want to give a couple other relations. So for PGL2, so PGL2, remember, that's just the thing tensor generated by the adjoint representation inside of rep Q PGL2. It's that category of rep Q SL2 generated by the adjoint. And so we have a similar diagrammatics because V2, tensor V2 has not just two summons, but three. So it's V0 plus V2 plus V4, whereas this one had only two summons. This is going to imply a more complicated diagrammatics. So in particular, we're going to have to allow trivalent vertices. So this is the sort of unique map from V2 tensor V2 to V2. But once we allow those trivalent vertices, the rest of the simplifications apply. And so so the Skeins module for PGL2 with parameter Q is the span of trivalent vertices, trivalent graphs. Modulo, again, some local relations. Those ones look like this. If I ever have a crossing, I can resolve it, but I get 3 terms. So I get the 2 terms that we would have predicted. Then I get a new term which involves a trivalent picture. And here A, B, and C are some polynomials included. That was example 1. Example 2. Okay, I'll be a bit more sketchy here, but for GLN and SLN, there's spiders and webs presentation. First proposed in a related setting by Cooperberg, and then by Kautis, Geometzer, Morrison. And the idea is very similar. You have you can reduce to just having oriented graphs with vertices of degree n, and what we should think is that, so in the SLN case, you've got the defining representation, and then this corresponds to the map from V tensor to the N to the trivial representation, which is the determinant. And for GLN, you just have to be a little bit more careful. You've got not the trivial representation, but the determinant representation. So this is the invertible representation, or one chart representation, and there's some local relations that you impose here.
So David, I think if you want to use this kind of, I mean, if you're using our approach, it would be you would only have trivalent vertices. You have potentially.
Yes, yeah,
Which I would say is like due to some other.
what maybe more.
In this generality, maybe Sakura.
Yeah, Deborah, okay. So let me add his name. So yeah, I just want to I wanted to put these names on the board just to say that the Skeins module that I'm studying is the same one that you guys were studying, the same that Greg is studying, and the same that Sakura studied. Okay. So right. So just one more bit of motivation, which is why these things are so important, is if Q equals 1, then the Skeins module, any 3 manifold, is the algebra of polynomial functions on the character variety of the 3 manifold. So the set of maps from pi1 of the 3 manifold G conjugation, and maybe equivalently the set of G local systems. M. Isomorphism. And so maybe let me just sketch why a diagram like this gives you a function. So this is the Wilson loop construction. Okay, so we have our 3 manifold. We have this network. Have you? So, and we have a local system, G local system over it. Call that E. Well, what we can do, so we have these labels. We have a representation V here, representation W here. We have a map F here, and so on. So what we can do is we can take the associated vector bundle to this local system, and we can restrict it along this edge. So along this edge, we just have the associated vector bundle V. Along this edge, we have the associated vector bundle W, and so on. And precisely at the vertices, we've given ourselves the information how to transition from one vector bundle to another. And so then what we can do is we can choose any point that we like, and we can take a big trace of a big operator, which is just the parallel transport along this network. And so taking traces of monodromies, its functions. And so when we turn on the queue, we're giving some sort of deformed Wilson loop operators in this theory.
You didn't see the algebra structure here?
Yeah, good question. So here there's an algebra structure on functions, of course, commuted multiplication. On a three manifold, that structure gets destroyed when we turn on Q. So in terms of these diagrams, if I have two diagrams, the multiplication of functions is just concatenating the diagrams. But you see, there's an issue if the diagrams have intersecting support, then I need to decide, do I deform this way or do I deform this way? And when I turn on Q, I don't have such a choice. So yeah, I want to emphasize that when Q is not equal to 1, it's just a vector space. It doesn't have an algebra structure.
I'm sorry, you gave here in the map one way, so who proved that this is?
Yeah, right. Thank you. So for SL2, this is Bullock, Roman, Kanya, Bartzinska, so I also want to put Sakura's name up here. My understanding is that for a general group G, this is folklore. It's not. It's not. I can't give you a reference.
Are there generalization to include punctures and boundary components?
Yes. Let me talk about what you do with boundaries now. Right. So if so before I talk about three manifolds with boundary, let me talk about surfaces. So to a surface, we have a category called the Skeins category. And so the Skeins category, let me draw some surface here. So you can kind of already guess what the objects will be. They're going to be finite collections of points on the surface with representation. So just what we did for a disk, now I do it on a surface. And then the HOMs, between pairs of objects are just the same kinds of diagrams that we've been drawing. What have you, modulo the same local relations. So it's the exact same notion. And then it turns out that so this is a construction of Walker. We have a 3D TFT. Which sends a three manifold to its Skeins module. And it sends a surface to the Skeins category. Just defined exactly like this. And so, well, what do you do if you have a three manifold with boundary? you get what's called a Skein bimodule. So if we write the oriented boundary as the union of an incoming and outgoing Skein module, then we get a bimodule. Which I'll just think of as a morphism from the Skein category incoming to the Skein category of the outgoing. Morphism in the appropriate sense. So it's not a functor, but it's a bimodule.
The morphisms there, those things are just going through the cylinder, right? Nothing more complicated.
These ones are, so that this is, so right, so sorry, this was me spelling out what the HOMs are from say X tensor Y to U tensor V tensor W. So this is a vector space. And there, indeed, it's in a cylinder. But what I'm saying is if I have any three manifold with boundary, I can use the same sorts of pictures to define a morphism between the Skein categories.
We're just going back
Yeah.
to this question about this isomorphism. Is it follow from your work with
For surfaces, it's a bit complicated. I mean, basically, yes, but I think it also followed from stuff that was done before us as well. So maybe we can discuss that after. Yeah. Okay. Okay, but now that we've got the definitions, I think the main thing I want to get across actually is a conjecture. So this is the Langland's duality conjecture. Gain modules. Okay, so conjecture, this is something that we've proposed with V, Gunningham, and Safronov. Okay, so let's let Q equal e to the I psi. So psi is going to be this parameter. And let's let QL equal e to the I psi L. And psi times psi L equal -1. So basically, I'm just naming two complex parameters, Q and its Langland's dual, and I'm naming them in terms of some auxiliary parameters, they're logarithms. Then we have, and let M be a closed oriented three manifold. Then the conjecture is we have an isomorphism between the Skein module for that closed three manifold and the Skein module for the Langland's dual group at the Langland's dual parameter of that same three manifold. Let me make a remark that by conjecture of Witten, which we proved with Gunningham and Safronov, these are finite dimensional vector spaces. when Q is generic. And I should have added that we have an isomorphism when psi and therefore psi L are generic. So if psi is generic, then Q is generic. So yeah, just one sec. So this conjecture is really visceral. These are two finite dimensional vector spaces. I'm asserting that they have the same dimension. They're defined in completely different ways. The group G and its Langland's dual have no natural homomorphisms between them and so on. And I'm proposing that nevertheless you get an isomorphism of vector spaces. There was a question.
Is there a reason you're hesitating to make the conjecture at the categorical level for the surfaces?
Yeah, just because yes, morally it's true at the level of surfaces as well. But let me by way of answering that question, let me point out that the isomorphism that we're proposing, okay, okay, at the vector space level, they're finite dimensional vector spaces over the complex numbers of the same dimension. So equivalently, I'm saying that you can find an isomorphism like this. However, sort of Langland's philosophy would tell you that if you want to find one which is natural, if you wanted to find an isomorphism which say respects the mapping class groups here and the mapping class groups here, the natural isomorphism is going to be really complicated in Q. Because, well, first of all, you see that there's this transcendental relationship between Q and Q check. So you would expect some kind of interesting special functions to appear in describing, say, transitions between basis vectors. So that's the first point. So this is a bit intricate, I think. At the level of categories, what you said is morally true, but in the same way that here we had to take some complicated limits of functions, the level of categories, you're going to have to contend with some kind of complicated limits of objects. And I'm not really sure if I know the right functional analysis to make a precise.
When you say at the level of categories, you mean for the extended 3-tool teacher?
Yes, Nita's question was about what if we had Skein categories attached to surfaces? Yeah, in fact, it's folklore expectation that this Skein theory extends all the way down to a point, and then the real conjecture is that the data that you assign to a point called rep QG and the data you assign to a point called rep QG check for the Langland's dual, that those are equivalent at the level of a point. That would sort of imply both of these expectations. Okay.
There's some easy relation between the categorical statement and geometric Langlands for surfaces.
Yeah, let me explain. Yeah, thank you. I've pointed some great questions in the audience. Let me explain what this has to do with geometric Langlands. But I'll be a bit brief. So so actually, let me first recall arithmetic Langlands very briefly. So for arithmetic Langlands, we study some number field F defined over Q, and we have what are called, I'll just be brief here, we have automorphic forms, and we have Galois representations. These are automorphic forms for G, Galois representations for the Langlands dual. And then this has a sort of analog for function fields. So say of curves X defined over FP, for instance. Now, geometric Langlands is sort of founded on the idea that you can study function fields of a curve over FP analogously to how you study well, let me say, right, so we just have a curve over C. And then here, function fields on the automorphic side, you're looking at sort of bun GX versus again Galois representations. There's a well understood story how to think about G bundles as some kind of version of perfect forms, and then this gets ported over to the geometric Langland story, where we're looking at D modules on bungee and putting that in equivalence with say some kind of strike co of log G. Thanks. Okay. So in geometric Langlands, you relate D modules on bungee to functions on bungee there. You relate the set of Galois representations to the category of coherent sheaves on the incoherent sheaves on the space of G local systems. G check. Thank you. Okay. And so with those two things on the board, there's a very natural question, which is what sits here. So this is called Vay's Rosetta Stone, relating function fields to projective curves, but there is a dictionary relating number fields. It's called the Mazur-Kapranov-Reznikov dictionary relating number fields to three manifolds. And I'm proposing that for Q generic, the thing that sits here is the Skeins module. That's the proposal. It's worth mentioning, especially in this crowd, that this whole story was understood in physical terms by Kapustin and Witten. So you had n equals 4, d equals 4, Susi gauge theory, just Yang-Mills, a certain twist. Given by a parameter psi in CP1. And if you think about it for a minute, it's kind of remarkable that this is a 4D theory. And what they did is they gave some heuristic to compute the category of surface operators of this 4D theory, and then the S duality tells you that the theory with parameter G and psi is its equivalent to the Langlands dual theory. And so unpacking that at the level of surfaces, they were able to see that you have these two theories. This is when psi equals 0, and this is when psi equals infinity. Well, side check is infinity. And they also explained how to turn on the parameter psi and get the deformed geometric Langlands conjectures of Stoyanovsky, Gates-Gorey, and I'm forgetting Fagan and Frankel. So lots of people have worked at this level, but it's kind of remarkable that even in the physical picture, they never really wrote about the Hilbert spaces for three manifolds. So what are the state spaces? So even in a physical sort of sense, they didn't give any sort of mathematical guesses what this should be. And sort of meta conjecture is that these Skeins modules are the state spaces of the theory.
Okay, maybe it still is worth pointing out that there is Rosetta isn't quite right? There is one more ingredient in here, which is X over FP bar. There's X over FP, but there's X over FP bar that should go in between.
Okay, yes, thank you.
And that's the thing that should be like the projective curve over P. And also like the fiber of a torus of a circle fibration.
Okay, thank you. Yes, actually, no, I'm glad you mentioned the fibration. You notice that the category number is off here. So here, this is well, I didn't say in much detail, but this is like a vector space of some kind of functions on this space and functions on this space. Whereas here we attach a category. And Menyang's reminding us that that's not so surprising because really what we did is we took this thing which is supposed to behave like a surface, we crossed it with a circle. We took some sort of trace, and so that's what compares these dimensions. So that also restores why we would have something like a vector space here.
There is also a category of where X people are.
And is
Gates correlation.
yes, right.
Just returning to the finite duality conjecture for Skein modules, what about it? There's also some kind of
Yeah, so
geometric lines, right?
so at Q equals 1, so definitely the way that I phrase it is not true. We're not proposing it at Q equals 1. And in fact, for Q equals 1, various people are working on understanding what the correct thing to do is. So that's corresponding to psi equals 0 and infinity. And I think the Skein answer is wrong somehow. It's only correct generically. At special values, there's more pieces. So that's related like to the you know that here I should write indco and I should have some nilpotents, some story about nilpotents. You need to somehow figure out what the correction is there. So somehow for generic psi, you don't have to worry about this filtration by nilpotents and stuff. Yeah.
But I mean, there should be like an analytic answer at like 1 or at 0 and infinity, where like at 0, you told me it was like functions on local systems. And then at like on the A side, it should just be some kind of like a floor, like homology group. But
That's
for
the kind, yeah, that's the kind of thing that various of us are discussing. Mostly I've been listening, but Pavel Safronov and Edward Witten and David Benzvi and Sam Gunningham have been including me on some emails where they discuss that sort of stuff. So yes. Yeah.
So Justin says that like you would want this space to be described as the Skein modules in particular are coming from a boundary condition and from a specific choice of boundary condition.
Yeah.
That sort of behaves uniformly at generic Q and very, very differently when through a 0, which is why that does the boundary condition just doesn't exist and the way you would want it at Q equals infinity. It's missing out.
Yeah, that's right. Yeah, right. So I should have, yeah, thank you. So I'll say that I'll follow up what Tudor said briefly, and then I kind of want to state a theorem. So these are equivalent as 40 theories, but naturally the Skein module is not the value of this theory on a 3-manifold. It's rather you should take the 3-manifold cross with the interval, and then you need to put some boundary conditions here. So Dirichlet on one side and Neumann on the other. And the issue is that when you do this Langland's duality, these boundary conditions are interchanged. So a priori, the Skein module should go to something where even if you have this equivalence, the boundary conditions get swapped. But then when Q is generic, it turns out that these boundary conditions are actually equivalent to one another, and so you can.
I'm sorry, could you explain it a little bit more? You associate a vector space to a 3-manifold, but now you have a full 4-manifold with the boundary, so you should get a number rather than a vector space.
Yeah, but yeah, that's true. So I think maybe, yeah, so yeah, sorry, maybe let me not put Dirichlet here. So just so let me leave this one open. Dirichlet gives you a pointing. You're absolutely right.
Now you're getting a vector in your vector space.
But then you're decorating Neumann with all possible Skein. You're decorating Neumann with a bunch of line operators and
Yes.
a bunch of vectors. Yeah, that's not.
Yeah.
Yeah, so it's the loop operators in the remaining thing. Thanks.
This is really happening in 5 dimensions. this picture?
No, it's still four, it's in four
You're
dimensions.
not saying the 4D theory, 5D theory.
But it can be converted to 5, according to what's on Kavanagh. This can be.
Yeah, maybe, let me not, let's talk about that over copy. Right. So I find these kinds of discussions convincing up to a point, and then I like to see some actual numbers. And so we were talking about this for years, and I certainly wasn't comfortable giving talks until we had some numbers, and so now we do. So this is with Cunningham, Bazrani, and Haiping Yang. So let G equals GLN or SLN. Okay, so the first theorem. We look at the dimension. By the way, do I stop at 50? Did I spend 5 minutes or?
No, you can go to.
So if I look at the Skein module on the 3 torus, it's a finite dimensional vector space. I can compute its dimension. And it turns out that this is the partition number of n. So the number of Young diagrams. It's n boxes. And if I look at the Skein module for SLN on T3, then this is a convolution. So I take the partition function, I convolve it with the cube function, and I convolve that with the Mobius inversion, which is to say that I take the sum of all ways of writing n as a product of 3 distinct integers of the partition function applied to D times E cubed times the Mobius inversion function of F. And just a reminder, the Mobius inversion is either 0, 1, or -1, depending on the factorization. Okay, so of course you can compute tables of these numbers from this formula. And then another theorem that we proved with Sam and Hubble in a separate paper, which both of these papers will come in the next 2 months, I promise, is that the Skein module for PGLN of the 3 torus, it has the same formula. At least when n is prime.
But where is Q?
This is for generic
Oh,
Q.
right.
Yeah. So, right, I should have emphasized this before. I went to all this trouble oops, I erased the conjecture, but I went into all this trouble of telling you precisely which Q is dual to which, that was just for the sake of plausibility. The isomorphism, the vector spaces have the same dimension for generic Q. That's part of our proof. So it means that we can just do a sort of combinatorial computation of the dimensions to compare those.
And you know what happens to the dimensions for whatever the non-generic things are?
Essentially, it's always infinite dimensional. So it's finite dimensional for generic Q. So the conjecture is that the bad Q are precisely the Q that are roots of unity. And certainly there it can be infinite dimensional.
And there's no conjecture for those values?
There are conjecture. Yes, we do also have a conjecture for those values. Let me say.
Since you set up the Q and QL carefully, it seems.
Yeah. Okay, that's fair. Let me just maybe make a remark. I'm not prepared to write it carefully. That will use the last 10 minutes. But for Q root of unity. So for Q root of unity, there's work of various people. So with, well, okay, really it starts with Lustig. Lustig gives a relation, let me just write it briefly, between rep QG to rep classical representations of H, where H is the metaplectic dual to G. So this is some refinement of the Langland's dual. So this is not an equivalence, but a relation. I don't want to say, well, the quantum Frobenius. And so, starting with that relationship, you can explore what happens for the Langland's duality at different Q. Essentially, what happens is that you get a line bundle. So you get the Skein module turns out to be the global sections of a line bundle on the metaplectic dual character variety, and you can compare those line bundles. So there is a story there to tell. Okay. All right, but in my abstract I said I would talk about DAHA. So the point is that the way that we prove these results is very much using the representation theory of double affine Hecke algebras. So, yeah.
D3 is just the S1 cross D2. Right?
Yes, exactly.
So you're computing the dimension of something for.
Yes, exactly. That's exactly how it's proved. So yeah, thank you. So what Nito is reminding us is that if I want to study the Skein module of T3, well, that's just the Hochschild homology, categorical Hochschild homology of the Skein category of T2. That's the notion of dimension is actual homology of the category. And essentially what we do is the following. So, right, so let me say what happens for GLN. So for GLN, we show that the Skein category of the two torus is generated, just as an abelian category, is generated by a single object. So remember I said, so we got the torus, I'll draw it with its usual identification. And more or less by definition, this category is generated by infinitely many objects, which are the infinitely many possible powers. I can take the empty object. I can take an object with a single dot, with two dots, with three dots, etc. And by definition, it's generated by this infinite collection. But what we show is that it's actually generated as a category by just one object, the empty Skein object. And this is only a generic Q. And so what that means is that the Skein category of the two torus for GLN is just Morita equivalent to the endomorphisms of the empty object. Okay, and now this turns out to be isomorphic as an algebra to the sort of trivial case of the spherical DAHA. So here, this is rank n DAHA, and we have the parameters here tell us that so for experts, the t, which is the quadratic parameter, is equal to 1, and the q is left open. Q is our q. Okay. So this we proved in a paper with just 3 of us, Sam and Monica Mezzarani, And I want to emphasize that so this bit here, there are two very closely related results by people here. I hope I don't butcher them. So if we replace rep q gln by the Humphrey category, then Morton and Samuelson have the same results. So they proved that if you take sort of the Skein algebra, which is endomorphisms of the empty skeins, that you get a DAHA. So our result is different than theirs in that so in the Humphrey, you have this extra parameter, which is essentially the polynomial interpolation of n. We specialize so we're working with finite n rather than sort of interpolated n. And in fact, for us, various corollaries of their theorem that they prove are false for us. Only this one is true. And also, Whitman, Mallet, can you help me with the other co-authors? Chandler. And Novarini, thank you. Sorry, I had this on my notes. Novarini, is that? Yeah, okay. So these folks showed that, okay, you again work with finite n, but you assume, you make an assumption that rules out this, our special case. They showed a similar result. So anyways, this is sort of a well understood picture that endomorphisms of this is the spherical Heck algebra. Basically, our proof uses the fact that when we send this parameter q to 1, we get something called the commuting variety, and its algebraic geometry is known, and so that lets us now turn on the q and make it generic. So that argument wouldn't work in either of their cases, and also their arguments don't apply for us. Okay, so anyways, it's generated by the empty skein. The endomorphism of the empty skein is the spherical DAHA, and then we need to compute Hochschild homology, and then I just assert that that's a computation that one can do. And so we just perform that computation combinatorially, and we get this formulas. For SLN, slightly more complicated. The SLN is generated by, okay, so we have the empty skein object. We also have the object with a single dot all the way up to n-1 dots. So it's generated like that. But fortunately, the inarity of the number of dots is an invariant. So this object has 0 Hom space with this object. Every object here has 0 Hom spaces between one another. The central character tells them apart. And so we compute the endomorphisms of this one, and again, it's an instance of a spherical DAHA. So this one gives us the DAHA for type for SLN. And we actually, in SL2, we can compute this one explicitly, but in general, we can't compute these. But then we're saved because the 3 torus has an action of SL3, SL3Z, and this descends to an action of SL3Z mod NZ, and we can use this action. So it just acts by mapping class group transformations here. It actually, if we descend it to Z mod NZ, it preserves the Skein relations, and then this thing acts transitively. So all of this complicated combinatorics with partition, with taking convolutions, is really just to account for the fact that you have the naive GLN answer at certain special values, and then you need to do some convolution to get the rest of them. Okay. That concept is fine, yes. So unfortunately, I'll stop there.